Hello everyone. First of all, I would like to thank the organizing committee for this opportunity. My name is Chouarfa Nouhaila, and today, in collaboration with Dr. Abdelilah and Dr. Ilias, I will present our work on sustainable IoT sensors and efficient measurements in aircraft maintenance. This presentation reflects part of my PhD research, which focuses on the integration of IoT technologies to support predictive maintenance in aviation. Introduction: Aviation is becoming increasingly digital and data-driven. IoT technologies are now widely deployed in aircraft to monitor components, improve safety, and reduce costs. Sensors measure temperature, vibration, pressure, and many other parameters in real time. This creates opportunities for better diagnostics and predictive maintenance. However, the growth of IoT also brings challenges related to energy, consumption, data management, and long-term sustainability. This is why our research focuses on how to make IoT systems more sustainable and more efficient for aircraft maintenance. Problem statements: Even with modern IoT, aircraft maintenance still faces several issues. Most sensors consume a lot of energy and need frequent battery replacement. This is not practical in aviation where access is difficult and maintenance must be minimized. Sensors also generate massive amounts of data. Transmitting and processing all this information requires a lot of bandwidth and computing resources. Finally, aircraft operate under harsh conditions: vibration, temperatures changes, humidity, and electromagnetic interference. These conditions reduce sensor lifespan. So the key problem is, how can we build IoT systems that are energy efficient, reliable, and suitable for predictive maintenance? Research gap. In the literature, we found several gaps. Many studies focus on IE algorithm, but not on the quality or efficiency of sensor data. Few works propose complete IoT architectures that include sensing, communication, edge computing, and decision making. Real aviation constraints such as certification, noise, vibration, and cybersecurity are often ignored. Sustainability, such as battery waste and energy reduction, is rarely considered. These gaps show the need for a more holistic and sustainable IoT approach. Research objectives. From these gaps, we established the following objectives: develop an integrated IoT framework for predictive aircraft maintenance, identify sustainable and low-power IoT sensors suitable for aviation, explore efficient measurement and communication techniques to reduce energy consumption, integrate edge and cloud computing for optimized data processing, provide recommendations for future IoT-based maintenance systems. These objectives guide the structure of our work. Today, aircraft have many sensors measuring engine temperature, vibration, hydraulic pressure, fuel flow, brakes, and even structural strain. All this data is collected in real time, either on board or in the cloud. This is the Internet of Things in aviation. IoT enables continuous monitoring, detecting early signs of degradation and preventing failures. Maintenance becomes predictive rather than reactive, reducing unexpected breakdowns and improving safety. Digital twins, virtual models of aircraft components, help engineers test failure scenarios without touching the aircraft. Challenges remain: data overload. Huge amounts of data need smart processing. Energy and environment. Sensors consume power and face harsh conditions. Cybersecurity. Connected systems are vulnerable to attacks. Legacy integration. Older aircraft systems are hard to integrate with IoT. To make IoT scalable in aviation, sensors must be sustainable. A sustainable sensor means low power consumption, long lifespan, minimal battery waste, lightweight design, and sometimes energy harvesting. Examples include vibration energy harvesting, thermal harvesting from engines, miniature solar microcells, or ultra-low power MEMS sensors. Lightweight wireless sensors reduce cabling, which reduces aircraft weight, and weight reduction directly saves fuel and reduces emissions. Sustainable sensors are not just an environmental choice, they are also operationally crucial for modern aviation. In addition to sustainable sensors, we also need efficient measurement strategies. These techniques are essential because they reduce the amount of data collected and the energy consumed. Adaptive sampling. The sensor takes measurements only when necessary. Event-triggered sensing. The sensor activates only when abnormal behavior is detected. Compressed sensing captures only the essential information needed for analysis. Sensor fusion combines data from several sensors for more accuracy. Edge computing processes data directly on board before sending it to the cloud. By using these techniques, we reduce communication energy, storage requirements, processing time, and power consumption. This makes the entire IoT architectures lighter, smarter, and more reliable. Applications in predictive maintenance. Sustainable IoT sensors directly support predictive maintenance. Real-time data identifies early anomalies. Machine learning estimates remaining useful life (RUL). Airlines avoid unnecessary component replacements. AOG events and delays decrease. Spare parts logistics become more efficient. Digital twins enhance simulation and failure prediction, allowing engineers to evaluate different scenarios without touching the aircraft. The final outcome is clear: more safety, lower costs, and smoother operations. Our proposed framework integrates sustainability and efficient measurement into a complete IoT-based predictive maintenance system. It includes sustainable sensor layer, low power, long life, and energy harvesting sensors, measurement optimization layer, adaptive sampling, fusion, calibration, filtering, edge processing layer, lightweight ML for fast anomaly detection on board, low power communication, LoRa BLE UWB, reducing bandwidth and energy use, cloud analytic, deep models, RUL, projection, digital twins, decision support system, maintenance recommendations and alerts. This framework aligns sustainability, efficiency, and advanced analytics into one coherent architecture. Results from literature. From the literature, energy-efficient techniques reduce sensor power consumption by 30% to 60%. Edge IE improves anomaly detection and reduces false positives. Energy harvesting is feasible for several aircraft components. Compressed, sensing, and event-triggered sampling reduce transmitted data by up to 70%. Predictive maintenance reduces unplanned events and improves aircraft availability. However, real challenges remain: limited large-scale deployments, certification constraints, cybersecurity risks, and integration with legacy avionics. This confirms the need for more real-world testing. For the current stage of my work, my focus is to develop, implement, and demonstrate a complete IoT solution that validates the concepts presented in this research. More precisely, I'm working on the design of IoT module for aircraft engine monitoring with the goal of achieving three essential outcomes. The first one, collect high quality and high precision engine data while ensuring that the sensing layer remains energy efficient and long lasting. The second one, optimize data processing by integrating lightweight algorithms directly at the edge to reduce redundancy, improve detection speed, and minimize communication costs. And for the third one, demonstrate the feasibility of sustainable sensing through energy harvesting techniques and low power measurement strategies specifically adapted to the aviation environment. This prototype allows us to test, in a realistic setup, how sustainable IoT sensors behave under engine vibration, temperature variations, and operational constraints. It also provides a foundation to compare different measurement techniques, such as adaptive sampling, compressed sensing, and event-triggered acquisition, and evaluate their practical impact on accuracy, energy consumption. The next steps include validating the module through laboratory experiments, integrating advanced anomaly detection models, and performed continuous optimization based on a real engine operation profile. Ultimately, this work aims to transform predictive maintenance from a concept into a deployable, real-world solution, supporting safer, more efficient, and more sustainable aircraft operations. To conclude, integrating sustainable IoT sensors with efficient measurement techniques offers a powerful solution for modern aircraft maintenance. This combination reduces energy consumption, increases reliability, and supports truly predictive maintenance. Our engine monitoring prototype with potential TCAS integration demonstrates real perspectives for improving both operational efficiency and flight safety. Thank you very much for your attention.